All right, now we're going to start looking with substitution rule on how you do definite integral. So when you if you have upper and lower limits now, how do you evaluate that? Well, you're still going to do your substitution and do that, but that also means we need to now make our limits in terms of this new function as well. All right, so let's look at an example. Here we want to integrate this function with substitution. Well, we've looked at some of these now already, and we know usually whatever's under that square root is going to be what we want to substitute. So let's put u equal to 2x plus 1 here. That means our derivative ends up being 2 dx here. That means we're going to have this extra 1/2 constant in this one. So substituting now, that means this is going to change into 1/2. This will end up being square root of u du, and we know we can integrate that now, but what we also need to change now is our limits. Before they were 0 and 4, but that was as a function of this 2x plus 1 function here. Now we need to change those in terms of our new function here, which is u. So what we're going to do is plug those numbers in for x and see what u comes out to be. So what I mean here is our new function, which was u equals 2x plus 1, we're going to plug in and see what does this function end up being when we put 0 in place of x, because 0 was one of our limits here. So what does that come out to be? Well, that ends up being 2 times 0, 0 plus 1 is 1. So now in our new function here, this is going to turn into a 1. We're also going to do that and plug in our other number here of 4 and see what this comes out to be. So if we do 2 times 4, that's 8, plus 1 is 9. So now our new upper limit becomes 9. And when we do that now, we do not have to go back and substitute in. This is a brand new integral that we can just solve from here. So let's do our next integration step. Again, though, they probably want to use this as an exponent of 1/2 to do the antiderivative, which would be 3/2 with a reciprocal of 2/3 here. We still have that extra 1/2 that we're bringing with. And now we're going to evaluate this at both 9 and 1. There's no reason now that we need to substitute back in for u, because we've changed these limits here in terms of this new function u. One thing I'm going to do, these two 2's can cancel out. So now we have 1/3. We're going to plug in 9 for this. So we got to figure out what's 9 to the 3/2 power minus what we get when we plug in 1 for that function. Okay, and I'm just going to leave that 1/3 outside of here, and so that we multiply it by at the end. Well, 1 to any power we know should be 1 here. We're going to have to figure out what is 9 to the 3/2 power. You could do that on the calculator. One other way to do it, if we have a 2 in the denominator of our exponent, that's like a square root. So that would mean that we're doing square root of 9, and then the top number is like an exponent, that would be like to the 3rd power. So square root of 9 is 3. 3 to the 3rd power should be, or should make that 27. And so now we have that this is 1/3 times 26, or we could write that as 26/3. And that would be the exact area under this graph. So if we go back here, if you take 26 divided by 3, that's going to be like 8 and 2/3. We got 1, 2, 3, 4, 5, 6 full squares. This is pretty close to 7. These two together here would kind of be 8, and then yeah, this is about 2/3 of 1, so 8 and 2/3 seems about right. Now, when we changed that to this other function, the area under this one right here should give the exact same area as that one we started with. So if you graphed out the graph of 1/2 square root of u, That graph looks like the one here. And now remember before it was from 0 to 4, 0 to 4 here. Well, our limits ended up changing to 1 and 9. And so if you find this area, this should also be about 8 2/3, the same answer. 1, 2, 3, 4, got 5 full squares. This little bit with what we're missing there would be 6. This would be 7 if you added in that little bit, at least pretty close. That would be 8 if you added this amount here, and then you got about 1/3 and 1/3, which is 2/3. Yeah, it's the same amount, 8 2/3, same answer we got. So you can see the new function, if you change the limits, then changes to a function that has equivalent area. Let's try another one of those. We want to integrate this one. Here, we could substitute for what's inside those parentheses there. X squared plus 5. Our derivative ends up being 2x dx. So when we substitute, that's all going to turn into a u. I see our 2x and dx here. That should both turn into our du. So now our new integral is just u du. But we want to change those so that we don't have to substitute back in. So what does our new limits turn to? It's not going to be 0 and 1 anymore. So what do you get if you plug in 0 in for this function? Well, it'll be 0 squared plus 5, which is 5. So our new lower limit is 5. What do we get if we plug in 1? So 1 squared plus 5 would be 6. And now our new limits are 6 and 0. So we want to integrate that with, 6 and 5. Now we want to integrate that with 6 and 5 instead of 0 and 1. If we do that here, our antiderivative is 1/2 u squared, evaluated at 6 and 5. The 1/2 we can multiply later, but let's figure out what we get when we plug in those two numbers. So 6 squared minus 5 squared. That's going to end up being 1/2 of 36 minus 25, which is 11. And so we get 11 times 1/2, or 11 halves. So the answer would be 11 halves, or 5 and 1/2. Okay. So once you change those limits, there's no reason to substitute back in. Why don't you guys pause the video and see if you can do this one. All right, let's see what you got here. Should have substituted for what's underneath that square root, x cubed plus 1. Our derivative here does match, and these should cancel out and just be our du. So now you're doing what's the antiderivative of u square root of u. Make sure you also change those limits. So if you plug in -1, new lower limit should be 0. If you plug in the top limit of 1, that should have came out to be 2. So those should be your two new lower and upper limits. Antiderivative, add 1 and then put the reciprocal. Now if we plug in those numbers, we should get our answer here. So now we got 2 to the 3/2 power minus 0 to the 3/2 power. 0 to any power is just 0. 2 to the 3/2 power, I don't think necessarily comes out to be a nice number. So you could either leave it as 2/3 times 2 to the 3/2 power. Otherwise, another way you could write that would be, you got 2/3. It would be, remember the bottom number is like a square root, so it'd be like square root of 2 to the 3rd power, which is the same as square root of 8. So you could write it like that. That is a square root. You could simplify. You could pull out the perfect square. There's a perfect square of 4 in there. Square root of 4 and square root of 2. Square root of 4 is 2, so you could also write it as 4 square roots of 2 over 3. So that answer or this one would probably kind of be the preferred ones there. This one's probably a little bit nicer of an answer. All right. Next one. Let's try one with trig. So here we see that we got tangent times secant squared there. So what are we going to what are we going to substitute here? Well, I think we know that if we put it equal to tangent, we know that the derivative of tangent ends up being secant squared, which I also see as secant squared over there. So that should work to change this through. So this would become our u. Secant squared, all this dx would become our du. So now our integral would become u du. But we also want to change those limits. So now what you got to do is go through and see what do you get when you take tangent to the pi over 4. And what is this going to be when you do tangent of 0 and plug those in? If you're not good with these, you can use your calculator here. Make sure, because it has pi in there, that your mode is on radians, not degrees. So you got to change that over. So if we do tan 0, we do get 0. So the bottom one remains the same because tangent 0 is 0 here. If you do tangent of pi over 4, tangent pi over 4, get 1 here, and so that's now 1. Now this should be a pretty easy one to do. Similar to the one we had before, that's 1/2 u squared, evaluated at 1 and 0. So we got 1/2 times 1 squared minus 0 squared. 1 squared is 1, 0 squared is 0, so the answer is just 1/2 here. The answer would be 1/2. All right, let's have you guys try one with trig here. So see if you can do this one. Looks like with what's in that parentheses, there's probably our substitution of x squared. So see if you can go through and try this one out. All right, let's see what you got. Derivative here would be 2x dx. If you move that constant over to the other side, we got an x dx here that should then change into 1/2 du. So there's our 1/2, there's our du. Antiderivative of cosine will be sine, but make sure you also change those limits here. So if you put in the bottom limit of 0, 0 squared is 0, pi squared is pi squared. So now if you plug those in, you get this. Sine of 0 is 0. That's just 0. Sine of pi squared, there's not really a way of evaluating that, so you just have to leave it then as that, and so your final answer should be 1/2 times sine of pi squared. There's not an exact solution to that, so if you want an exact answer, just leave it as that. All right, hopefully you got that. Next one, let's take a look here. You know, if there's powers involved, that's probably what you want to substitute for. So here, 8x minus 7 would be what we'd substitute. Derivative here would be 8 dx. That means we're going to have this 1/8 constant on here. So like we've seen before, you can pull out that 1/8. I also see a constant here of a 4 that we could pull out. So now this just ends up being 1 over u to the 4th du. The 1 and 2, though, we got to change those. So what do those change into? So if you were to plug in 2, what's that? We're going to get 16 minus 7 is 9. If we put in the lower one of 1, we get 8 minus 7, which is 1. So our new limits here would be 1 and 9. So 4 times 1/8, well, 4 goes into 4 once, 4 goes in here twice, so now we got a new constant of 1/2. Also, this would be easier to integrate if we think of this, move it up to the numerator as an exponent of -4. So now add 1 to that. Adding 1, make sure it go to -3, because if you add to a negative, it's going to become less there. Reciprocal of that would be -1/3. But we also have this constant here of 1/2 still multiplied to that. We want to evaluate this at 9 and 1. So to keep going here, I'm gonna multiply those two constants together to get -1/6. Also here, if you got that u to the -3, that's the same as 1 over u to the +3 power, evaluated at 9 and 1. So now if we put those numbers in. We're going to get 1 over 9 cubed minus 1 over 1 cubed. 1 cubed is just 1, so that's just going to be minus 1 here. You're probably going to want to use calculator to figure out what this is going to be. 9 to the third power is going to be 729. And so now see what that equals. This is probably easier to just use with calculator. So if I'm entering this one in, you can just enter it in exactly how it looks. Negative 1/6 times, we got 1 over 729 minus 1. And that's going to give you probably as a decimal answer, yep. But to change it to a fraction, if you hit math, and then this first one here, fraction, and hit enter one more time, it'll change it to a fraction for you for an exact answer. So looks like the exact answer to this becomes 364 over 2,187. So that would be the exact area under that graph. Okay, looking at these ones here, trying this one out, you got to keep in mind that integrals, even with the substitution, still have to work with what we talked about with your limits here. You can't have, it has to be continuous on this function. In this one, you would get caught here because there's one number that x can't be on here. Remember, if you're dividing, your denominator, whatever this is, can't equal 0 here. Otherwise, we have something over 0, and you can't have that. So what number would make that equal 0? If you were to set 3x minus 5 equal to 0, add 5, divide by 3, it means that when x equals 5/3, that denominator equals 0. 5/3 is the same as 1 2/3. Well, would we pass through 1 2/3 on the way from 1 to 3? Yeah, this function is not continuous here on the interval from 1 to 3. And so this is one of those, again, even though we're doing substitution, we can't do this one and get a significant answer. Integration won't work here. So this is one where you would not be able to do a solution on this one. Now, if we would do that same function but change these, now let's say we're doing it from 2 to 3, now we'd be okay. If we're going from 2 to 3, we don't pass through 1 2/3. This one would be solvable. So I want you to try this one out. See if you can solve this one using substitution here where we set it equal to the bottom. So pause the video again, try out, see what you. All right, let's see how far you got here. If you substitute here, derivative is 3, so you're going to end up with this extra constant of 1/3 out here. We want to change our limits, so put in both 3 and 2. You're going to get new limits of 1 and 4. And then we got our u in there. Now, one thing as you're doing these, sometimes they write these integrals like this where you got that dx, kind of they put it on top here. Well, that can easily just be moved outside of here. So that dx is over here. But then what it would be on top, we got to have a placeholder then of 1. So this is like a 1 over u du. So to find antiderivative, that's that one we know is going to be natural log, because derivative of natural log is 1 over u. And it would be with absolute value here. And we'd have that 1/3 still there, evaluated at 4 and 1. So now we got that this is natural log of 4 minus natural log of 1. Natural log of 1, if you do that on your calculator, is 0. And so the answer here is just going to come out to be 1/3 times natural log of 4. That would be the answer. That's perfectly acceptable. If you were checking this in the back of the book, they might possibly use some of those natural log properties we have. Remember, if there's a number in front, you could also move that up as an exponent of 4. So it would also be equal to natural log of 4 to the 1/3 power, which you could also write as natural log of the cubed root of 4. So they might write it like that. Either one of these is a good answer for that one. So when you have When you have definite integrals, you want to change those limits, so you change the function.